Hi, thus far we were discussing first order difference equations. And to be exact, we were discussing first order difference equations with constant coefficients and mostly with constant term. However, we discussed what we can do in the cases of variable term, and we can use the method of undetermined coefficients. However, difference equations can be in nonlinear form. Like in this equation, we see that yt is to the power of 3, here yt is in sine and in natural logarithm. Look, in this case, in these cases, solving the difference equation is becoming very, very troublesome. However, just like in case of differential equations, here we can use a method that was proven to be very convenient in the context where finding exact solution is very troublesome. So we're going to use phase diagram, this time for difference equations. Now look, each of these different equations can be transformed. For example, I can move all the expressions with yt to the right hand side, and look what I'm getting. Yt plus 1 equals to negative yt to the power of 3 plus 5. Or here, I'm getting that yt plus 1 is equal to negative sine yt plus ln yt plus 3. Look, I haven't done much. However, I transformed these expressions into the form where yt plus 1 is expressed as a function of yt alone. And look, yt plus, in this form, yt plus 1 equals f of yt. So this is a very similar situation to the one we had when we were dealing with differential equations. On one hand, we had derivative, and this derivative was expressed as a function of the variable alone. And look, we can use similar tools to analyze the concept, to analyze the convergence in the case of difference equations. However, look, this function here has a very specific purpose. Look what it does. This function here transform observation from yt into a new value, yt plus 1. So in this case, we need to use a slightly different trick in order to deal with phase diagrams. And look, we need to consider different cases. We're going to start with two very simple ones. And let me explain what do I mean. When we deal with phase diagram for difference equation, look what we have here. On a horizontal axis, we've got yt. On vertical axis, we've got yt plus 1. So look, this graph is showing us how yt changes into yt plus 1. And look, the function that is doing so is given over here. So this function tells you that if yt over here was this much, then the next period is going to be this much. Now, as you might notice, I also draw a 45 degrees line. Actually, as it turns out, this line proves to be very helpful over here. And we should notice one specific thing about this line. Look, each point on the 45 degrees line represents a combination where yt is equal to yt plus 1. So they have the same values. Where can we expect such a situation? In equilibrium. So look, over here, and as well over here, we should expect the equilibrium because this is the point where value of yt and yt plus 1 are the same. So if we are at this point, we've reached the intertemporal equilibrium. Okay, now, as you might notice, I've added here one additional assumption. This additional assumption basically states that first derivative of the function that connects yt to yt plus 1 has a slope lower than 1. Of course, 45 degrees line has a slope of 1, right? This one is flat, right? Let's see what happens in this context. Look, what happens if variable yt at some point 0 is this much. Look, from the graph, I can read that the value of this variable in the next period is going to be this much. Right? Because this is what this function tells me. This function tells you how do we get from past value to the future value, from present value to the future value, right? Now, how is this? So now, if I know that y is equal to y1, how can I know how much it's going to be next period? And look, the answer is kind of easy because look, we can use this. And look, we know that at this point, y1 is reflected over here, right? So, if y1 is this much, then y2 will be here. Okay, but if y2 is over here, I can use it to put it over here. And then I'm going to be able to read y3. And look, this is why we actually are using the line. Look, the line is allowing us to track what is happening. Look, first we start at y0, and y0 will change into y1. Then we can plot this y1 over here, because y1, y1, and we can see what will happen next. We will see y2, and y2 over here can be found. And look, what do we see over here? When the line, when the function you got is flatter than 45 degrees line, so we've got, so its slope is somewhere between 0 and 1, what do we get? We get time path that is convergent and what can we else say about this time path? Look here, higher value, higher value, higher value, higher value, right? Which means that this time path is non-oscillatory. Okay, so look, we see that regardless from which point will we start, on this side of the equilibrium or on this side of the equilibrium, we will always end up in equilibrium. So look, if you see a phase diagram like this, so you see that the function that connects yt to yt plus 1 is upward sloping, and its slope is between 0 and 1, we will have convergent and non-oscillatory time path. Okay, let's see, however, what happens if the opposite is true. What if now this function is steeper than 1? Well, we can easily check it. Okay, let me just change the color. Okay, so let's just say the value of y is y0. Now, from this value, from this function, I can read what is going to be y1. And now, look, if I've got y1 over here, I can put it in here. And from here, I can read to what y1 is going to change, y2. Then, I will be able to read y2 over here. And then, let's just say somewhere over here, I will be able to read the yt plus 1. And look, what do we see happening over here? First, we're moving here. We are very close to equilibrium, but then we move to the right, and then we go up. Then we move further to the right, and then we go up. Then we would move further to the right, and then we would go up even further. So, this should tell us about the second case. Look, in the second case, regardless where we start, unless we are exactly in the equilibrium, we'll see we'll be getting further and further and further away from this equilibrium. So this time path is divergent. However, look, we've got bigger value, bigger value, bigger value, bigger value, and bigger value. So this time path is divergent and non-oscillatory. Okay, so knowing this, we can move on to two cases we have not considered. Well, of course, look, we were considering only functions that were upward sloping. Now let's consider a case where the function actually is downward sloping. Okay, we assume that this is 45 degrees line, and this is the function we're talking about. Look, again, this f3, I can make some assumptions. I will assume that its derivative is negative, but somewhere between -1 and 0. Maybe I'll write it properly as a function of yt equal is somewhere between -1 and 0. Okay, again, let's see what happens. Now, let's just say that we start at point y0. From point y0, we can read what is y1. Now, moving to the line, we will get the value of y1 over here. However, if y1 is over here, from here we can read y2. Now, if y2 is over here, it will be over here. However, if y2 is over here, from here we can read y3. But if y3 is over here, y3 is over here, then y4 is over here. But if y4 is over here, okay, I hope you can see the pattern. Okay, let's start how we were going. First, from y0 to y1, we went here. Then we got y1. And look, let's notice one thing. We were below the equilibrium, that equilibrium that is over here, right? And now we are above. Okay, but then what happens? We can see from here that now we are going to be below the equilibrium. However, now, look, too far. Okay, let's make those dashed. So look, we went above equilibrium, and then we went below equilibrium, right? And now this y3 is above equilibrium again, right? So where can we expect to be later? Well, we would expect to be here, then here, and then here. So look, what is happening in this case is that we are actually getting closer and closer and closer to equilibrium. However, value of y is below, above equilibrium, below, above, below, above. So in this case, we've got a time path that is in one case convergent, and on the other, oscillatory. Okay, now, finally, the last case is what would happen if we would have a line that is downward sloping, however, our F4 has a slope that is lower than -1. What does it mean? It means now that the function is falling faster than this one, right? And let's see what are the consequences. Let's see what are the consequences of that. So, okay, I think this one is the color of characters. Again, here is the equilibrium. Now let's see what happens if we are starting somewhere slightly below the equilibrium. Okay, so we see that from y1, y0, we go to y1 over here. But if this is y1, we are ending up over here. Now, from the line, we can read y2, and we can put y2 over here. From this y2, I can read y3, and I get this y3 over here. And I know that for this y3, this is going to be y4. And, okay, let me just use a different color to denote this. Look what is happening here. We start very close, right? And now we move to y1. We are above, we are below the equilibrium. Now we are above. And as you can see, we're actually moving further and further away from the equilibrium. And this time, we do it in an oscillatory manner. So look, this last case actually covers the situation when the time path is non-convergent I'm sorry, divergent, of course. And oscillatory. So look, based on these four cases, we see that only functions with the absolute value of the slope, somewhere between 0 and 1, can produce convergent time paths. However, we should notice the second thing. Only positively sloped lines will produce non-oscillatory time paths, and only negatively sloped functions will produce oscillatory time paths. Okay, this is it about the phase diagram. In the next video, we're going to see some examples of economic problems in which we actually use this phase diagram. Take care and see you in the next video.